If not, let's go on to dielectric waveguide or dielectric slab waveguide. And this waveguide is more interesting because it needs no metal part. It can be made out of dielectric region, which could be glass. In the case of optical fiber, the fiber is made of glass, and then you can have guidance. And guidance happens because you can pick the material such that there is total internal reflection happening at the top interface. There's total internal reflection happening at the bottom interface. Then there's no energy leaving this guided region. The wave just bounces back and forth and get guidance, okay? So it's easier said than done. A guidance condition can be written down easily, but then doing the math is a bit complicated. And we prefer to study this waveguide because it is one-dimensional. It is actually very simple. So we can teach this in a course. But the true waveguide that you have in the present world that is dielectric is the optical fiber. And this optical fiber has essentially changed our life or changed the way we communicate with each other, because you can send an optical signal on an optical fiber. Because optical signals have very high frequencies, it has very large bandwidth. The bandwidth of an optical fiber is huge. And the moment we can communicate with each other using optical fiber, we have a huge increase in the bandwidth of our communication system. Remember, the first technology came about with radio wave. Okay, radio wave those are kilohertz, megahertz. And then after that, we developed technology for microwave. Okay, there's gigahertz. Okay, and then optical wave is maybe 1,000 terahertz. Okay, they are quite high in frequency, and hence the wave is very, very short in terms of its wavelength. Because of the impact that optical fiber has in modern life, actually Charles Kao, who invented the optical fiber, was given the Nobel Prize in 2009, Nobel Prize. Okay, but the optical fiber is quite hard to study because you need Bessel functions to study optical fiber. So we would use just a dielectric slab waveguide. Okay, in the dielectric slab waveguide, you don't need Bessel function. You just need sinusoidal functions, because the wave that bounces back and forth is a sinusoidal function. And we can write down the guidance condition for this waveguide using what we have learned. Okay, so the guidance condition would be 1 is equal to R10. Let's assume that the reflection coefficient at this interface is R10. And then the other reflection coefficient is R12. Then we track the transverse phase. And let's assume that the transverse phase is changing in such a manner that after the wave bounces 2 times around, the total phase that it accumulates is given to be that. Okay, and it has to become itself. Whereas D, as you can see from this picture, is the thickness of the dielectric slab. Okay, and as I said before, when you have total internal reflection, all this would become just 1. And this equation can be satisfied because, as you have learned before, at total internal reflection, Rij is of the form of A plus Jb over A minus Jb when total internal reflection occurs. And hence you can easily convince yourself that when this is the case, then the magnitude of Rij must be 1, because the numerator and the denominator are just a complex conjugate of each other. There's the same complex number, but complex conjugate of each other. Okay, so when we have total internal reflections at the top and the bottom interface, then guidance is possible. Okay, and to make things simpler, we will make R12 to be the same as R10. Okay, so which means that we will say mu2 is equal to mu0, epsilon2 is equal to epsilon0 to simplify our life. And that you know what R10 is for the TE case. For the TE case, if I were to say that we're only studying the TE case here, R12 would be equal to mu, let me see, it should be mu0 beta 1x. I have a coordinate change over here because now I call this the x-axis instead of the z-axis. So this thing should now be called beta 1x and beta 0x. Okay, instead of beta 1z and beta 0z. Because of my coordinate change. This is mainly due to convention. Due to the convention that when we study waveguide, we assume that the direction of propagation of the wave is usually z. And because we have to adhere to convention, we change the definition of the Fresnel reflection coefficient by changing from z to x. Okay, before that, when we derive this Fresnel reflection coefficient, the axis vertical and perpendicular to the interface is called the z-axis. Now it's called the x-axis. Okay, so how can we solve this equation? It looks rather complicated. Okay, for the TE case, we can say that, well, R10 is equal to something that has a Guth-Hessian shift in it. Okay, that has a Guth-Hessian shift in it. And then if you look at for the face of this numerator, it will be arctangent of B over A using simple complex analysis. And then this would be minus the arctangent of B over A. Okay, and you can work this out quite easily using Fresnel reflection coefficient that we have just written down on the previous slide. Okay, that Fresnel reflection coefficient is this. And when you have total internal reflection, this beta 0x becomes an imaginary number. And this reflection coefficient would have an amplitude of 1. So I'm going to say that, well, beta 0x is going to become an imaginary number. It's going to be just this imaginary number. And if you plug in the correct numbers now to look for the Guth-Hessian shift, you'll find that this thing over here is e to the j theta te, and that phase is actually equal to e to the 2j because of the 2 times that it happens, arctangent of the ratio of the complex number, the imaginary number, to the real number. Okay, if you look at this and if you look at the previous one of this becomes a pure imaginary number because of this change. And if you look for this phase, then the phase is just that over there. And this is the phase shift. Now, of course, we have learned this to be the Guth-Hessian shift before when we study total internal reflection. Okay, so how do we solve this problem? In order for guidance to occur, we say that R10 square times e to the minus 2j beta 1 x d must be equal to 1. Okay, that is the transverse resonance condition. And if you square this, okay, and take the phase of that, you will have, in order for this phase to be equal to 1, this equation to be equal to 1, it must be for the arctangent. I put a factor of 2 in because of the squaring, so that becomes that one. Okay, mu 0, beta 0, beta 1x. And let me make this one. This must be equal to 2n pi. Sorry, there should be this phase of 2 beta 1x d must be equal to 2n pi, because I can write the right hand side as e to the j 2n pi. Okay, so I match the phase, right hand side and left hand side. I should have this as my equation for guidance. In order for this equation to be satisfied, this has to be true. And this equation is not easy to solve, but it can be solved nevertheless. So what we need to do then is actually to divide this equation by 4. Okay, the trick is to divide this equation by 4. Okay, and if you do that, then this factor of 4 will go away, and you would have arctangent of this being equal to the rest divided by 4, and then you take the arctangent away by taking the tangent of the equation. Okay, and then on the other side, you have something divided by 4, so it will become n pi over 2 plus, because it divided by 4, you take this to the other side, become beta 1x d over 2. Okay, and then because you take the arctangent from the left-hand side to the right-hand side, you have this equation over here. Can everybody follow the derivation that arrives at the bottommost equation? Okay, so it's quite simple. If you can't follow, you can actually go to the algebra and arrive at the bottom equation. So this equation is difficult to solve. It is the kind of equation that we say that is implicit. It actually is transcendental. Somebody would use that term, transcendental, and no closed form solutions. So one way to solve this equation is to use the graphical method. Okay, so graphical method allows us to solve this equation. You can also kind of intuit that you can set n to an even number and an odd number. You will get two different sets of equations to solve. For instance, if I set n to be an even number, okay, this is just pi over 2, and then maybe pi and so on, then this equation would just become a simpler equation in a sense. So when n is equal to even, the transcendental equation that I have becomes something like mu1 alpha 0x is mu 0 beta 1x tangent of beta 1x d over 2. Okay, and this thing just disappears. I'm using the fact that if you're familiar with the tangent of the theta function, if you just plot tangent as a function of theta, it looks something like this, that when theta is equal to pi over 2, it goes to infinity, and then it becomes something like this. And then this is pi over 2, this is pi, this is 3 pi over 2, and so on. So if you are at the case where n is even, you will either hit this point, or this point, or this point, and you can all replace them with the tangent. Okay, it's just a periodic function, so you don't have to write over again. However, if n is odd, what you have then is that this factor that you have here will be pi over 2. Okay, you shift the thing by pi over 2, or 3 pi over 2, or maybe 5 pi over 2, and so on. So you hit the infinity values. Okay, and then you hit the infinity value so that this equation can be written as a cotangent of something. So it will become 0x minus this, the sign flip, because actually hit infinity at the place where it changes sign. So you have two simplified equations to solve, in a sense, either when you pick n even or when you pick n odd. And this still cannot be solved easily. So what you need to do then is to find graphical methods to solving this equation. And what you find eventually is that when you pick n to be even, the guided modes will look something like this. The guided modes would be a standing wave inside the dielectric slab waveguide, because it corresponds to waves bouncing back and forth between these two interfaces. It is due to total internal reflection. The wave bounces back and forth. And because of total internal reflection, the wave is evanescent outside. Okay, and then you have odd mode, where the field profile is an odd function of x, and then you have the even mode, where the field profile is an even function of x. That detail I will not go into, but if you look at the solutions, that is how they look like. The most important thing is notice that the waves are evanescent outside. They're evanescent outside, so the wave is exponentially decaying outside. And because of that, the energy of the wave is being trapped inside the dielectric slab waveguide, and that's how guidance comes about. Okay, so the next thing that we should look at is how to solve these equations graphically. Okay, it turns out that to solve these equations graphically, I have to do some work some more. I have to convert this equation so that it is amenable to solving by the graphical method. Okay, so it turns out that since the right hand side is a cotangent as a function of beta 1x, okay, and then it's a cotangent as a function of beta 1x, it is easier to solve this equation in terms of beta 1x variable instead of some other variables, because you know that alpha 0x is actually something that comes from, beta 0x becomes j alpha 0x. So you know that beta 0x square by the dispersion relationship in region 0 would be equal to beta 0 square minus beta z square. Okay, and then you know that region 1, you will have this to be true. And beta 0 is the same. It's same every region due to phase matching. And because of these two equations, you can subtract the two equations to eliminate beta z and express beta 0x as a function of, you can subtract the two equations to express alpha 0x in terms of the thing. And if you subtract the two equations, then you will have something like beta 1 square minus beta 0 square minus beta x squared. Okay, this should be beta 1x squared, sorry. If I just subtract the two equations, I will get this equation. Okay, then this should be a minus sign here. And I'm going to do this trick and then multiply this equation by d over 2. And so that what I have will look like something that this factor is the same as that factor in the thing. I'm also going to multiply this equation by d over 2. Okay. And I'm going to, of course, write my alpha 0x using this equation over here. So everything will be in terms of beta 1x. So only variable I have in my equation is beta 1x. Okay, because beta 1s cannot be changed. Beta 0 cannot be changed. Only this number can be changed. And when I plot this thing, I keep that in mind. Okay, I keep that in mind. What I have then is that I can plot the left-hand side and the right-hand side of these two equations. Okay, left-hand side and right-hand side of these two equations. And at places where the curves meet each other, those are the solutions to this highly complex dielectric waveguide problem. So what I have done here is actually to plot the left-hand side. Okay, left-hand side is actually this equation over here. And as I point out before, left-hand side, after you multiply by d over 2, is given by alpha 0 x d over 2. Okay, I'm going to assume that mu1 and mu0 are the same. Okay, I'm going to assume that mu1 equals to mu0 to make things simpler. So the right-hand side is just alpha 0 x d over 2. Okay, and if I write it out in gory detail, what alpha 0 x is given by this equation over here. But because I multiply everything by d over 2, I bring the d over 2 inside the integrand, or not the integrand, inside the square root sign, I get d squared over 4. So the left-hand side will look something like this. So this is the left-hand side. Okay, for both of the equations. Okay. And then the right-hand side would become either this term or that term. Okay, so I will call that y1. Okay, actually I still kept my mu0 and mu1 here. Actually, they usually should just be equal to 1. So for the first equation, I will get something like this for the right-hand side. Okay, and then for the second equation, I will get something like this on the right-hand side. So I can plot y1. These are the plots of y1. They are something that looks like the tangent function, except that it's been modulated by this beta 1 xd. So it still looks very much like the tangent function. Okay, and then when I plot y2, I get this expression over here, and these are the y2 plots. Okay, it has the interesting fact that when beta 1 x d is equal to 0, this thing goes to infinity. But then because it's multiplied by this factor over here, this thing tends to a finite value. So y2 would look something like this, and this is another plot for y2 and so on. So the even and the odd solutions are given by these different plots, and the point where the left-hand side plot meets the right-hand side plots are the solutions of these transcendental equations. Okay, these are the graphical methods to solving this problem. But actually, these problems can be solved by a computer very easily. But graphical methods still offers you physical insight. Okay, so are there any questions on this graphical methods before we talk about the physical insight we can intuit from these plots? Okay,
Professor?
Yes?
Does that mean that there will be only TE0 and TE1 mode there? Like
yeah, for this particular problem, for this particular plot, there are only two solutions. But the problem I have here is that this is the equation of a circle. I don't know if you can see that this is the equation of a circle.
Yes.
So if I write y3 square equal to a constant square minus x square. Okay, if I write this being x square, and this is y3 square, you can see that this is an equation of a circle. That's why when I plot the left-hand side, I get a circle. Okay, because the variable here is my x. Okay, and the vertical axis is my y. Okay, so you can change the radius of this plot, and you will have more solutions. How can I change the radius of this plot? I can change the radius by increasing the contrast between the inside and the outside. I can increase the frequency, or I can make the dielectric slab thicker. So there are three liberties that I have to increase the radius of the circle. And if the radius of the circle is bigger, you can see that I can pick up more and more solutions. Can you see that? So when frequency is higher, I will find more trap modes. These are the trap modes inside the dielectric waveguide. Okay, and so the graphical plot and the graphical solution offers you physical insight in the sense that by increasing the contrast, increasing the frequency, increasing the size of the dielectric slab, you can find more and more trapped modes. Okay, and also there is a mode, TE0 mode, with no cutoff, which means that no matter how small you make the frequency, the smaller the frequency is, the smaller the radius of this thing. But no matter how small the radius of this circle is, there's always a solution. Whereas for the TE1 mode, if you make the radius smaller than a certain value, okay, then you wouldn't get a solution where alpha 0x is a positive number. You actually want a solution where the alpha 0x is a positive number so that the wave is evanescent. So if you find a solution where alpha 0x becomes negative, there's a no-no. That is a solution where you don't have evanescent wave outside the dielectric slab, and the mode is not guided. Okay, so are there any questions on this? So we can gain some physical insight by looking at graphical solutions, even though we have computers these days which can solve these problems really rapidly. So let's use the physical insight that we have gained to see how the dispersion diagram of this guided modes would be like. We say that when the frequency is very low, okay, when the frequency is very low, what you find is that the mode has very long wavelength, and most of the energy of the mode is actually outside the waveguide. Okay, you find that alpha 0x becomes very small. Alpha 0x becomes very small means that the mode is hardly trapped. It's weakly evanescent outside. Okay, that's what happens when alpha 0x is very small. So in that case, the phase velocity of the wave resembles that of the outer medium. That is, we have a dielectric slab waveguide where this is mu1 epsilon 1, this is mu naught epsilon naught, mu naught epsilon naught. So the phase velocity as well as the group velocity, if you take the derivative of this d beta versus d omega, that gives me the group velocity. And because the energy of the wave is outside, so you have group velocity and phase velocity approaching that of the outer medium. What happens if you increase the frequency? If you were to increase the frequency, you'll find that you find solutions where alpha 1x or alpha 0x becomes bigger and bigger. Okay, they move up this thing and become bigger and bigger. That means that the wave is more tightly trapped. Okay, it's evanescent strongly outside, and the mode is strongly trapped inside the dielectric slab. And if the mode is strongly trapped inside the dielectric slab, it will approach the group and the phase velocity of the dielectric slab. That is the kind of physical insight we can gain by looking at the solution. And DM case, you can get this by using duality principle. Okay, so I will not go into detail, but physics is very similar. And these are some of the plots from Professor Kong's book. He shows that TE and TM modes are very similar. Okay, and that at cutoff, these are the cutoff frequencies of those modes. The group and phase velocities are very similar to that of the outermost medium. Whereas if you increase the frequency, the group and phase velocity approaches that of the core, the innermost region, okay? And the plot of the guided mode will look something like this. You have odd mode and you have even modes, okay? And all this will be written out in great detail in the lecture notes. So are there any questions before we end today's lecture? This is an important topic because the physics that we see here is the same physics as that of an optical fiber waveguide. Total internal reflection when the fiber becomes bigger, we have more track modes. And when you are close to cutoff means that the wave is weakly evanescent outside. Okay, the wave is weakly evanescent outside. Then the wave actually reaches the group velocity of the outermost medium. As you look at this plot, okay, even the TE1 mode, when you're close to cutoff, alpha 0x is 0. Alpha 0x is 0 means that we don't have any more evanescent wave outside. Then all the energy of the wave is actually in the outer region, and hence giving rise to this kind of dispersion diagrams that we see here, as well as this kind of dispersion diagrams that we see here. Okay, are there any questions?